Okay, thank you, Ted. And I also have some messages from water, following from Michko's wonderful presentation. But the messages here are a little bit different. The message here is scientific. And so I hope you'll bear with me for some scientific points. And the science is actually what's the scientific nature, what's the real nature of water. And most people think that it's absolutely impossible that everything that there is to know about water isn't already known, because it's the simplest molecule and the most abundant on the face of the earth, and scientists have been studying water for a long time. And I want to first start by making the point that it's quite true that there are many things about water that we don't know. And so first I'll challenge you with a few slides, and I ask you, if you can, to explain what's going on here. And if you can't explain, then you have to agree with me that we don't really know everything there is to know about water. So here's something that you see all the time, right? And probably you don't ask too many questions about it. You've got the water. The water is evaporating all over. And sometimes you see a single solitary cloud. And so you have to ask yourself, if the water is evaporating from all over, how is it possible that you get only a single cloud? What about the stuff that's evaporating from here? Probably you never thought about that. Anybody know the answer? Okay, good. The answer is, if you don't know, that's good. Or someone knows the answer? Okay, so we'll get back to that later. Now here's another one. So when you have a water dropping on water, and you've had this experience quite a lot, the water that drops coalesces with the water at the bottom instantly, right? Well, here's an example where it's not so instant. The video shows, so we have water in this little pipette here. It's dropping on water, and you can see that the droplets persist for some time. And we've seen droplets persisting for up to 20 seconds or so on the water. Explain it.
Vibration. When they go into the tube there, they got a spiral. And it started vibration in it. So
why would the vibration prevent the coalescence?
Must be something scientific.
well.
Something. When the inner tube started to spin, that's the vortex.
Yeah.
There must be something that is still running inside the bubble, the water drop.
Well, it could be. You can also see this, however, in the rain. So if you look carefully, and I've looked carefully, when my student told me to start looking, you can see a puddle, and the rain falls, and sometimes you can see the droplets of rain persisting on the puddle. There's no vortex there. At least I don't think there's a vortex. So, okay, anyway, we'll get to that later, and perhaps you'll agree or disagree about the answer.
They're buddy drops. They're like
buddies. Yeah, okay, well, there may be some intention here. Okay, now here's a third one, and this comes from a different laboratory, but we've repeated it. So you take two beakers, and you put the beakers lip to lip, and you fill them with water. That's fine. And then you stick an electrode in each one, and you put a high voltage between them. And here's what happens. So the first thing that happens is the water forms a bridge between the two. However, if you move one beaker away from the other using a motor, you can see that this bridge persists. And it persists essentially indefinitely, and it persists for a distance of up to about 4 centimeters. This ain't water. I mean, how do you explain what's going on? You've never seen anything like this. Okay, so now that I've tempted you, I think I've demonstrated to you that we don't really know all there is to know about water, because if we did, you'd have answers to these right away, definitive answers. So I started my own interest in water with this book, which was written in 2001, and was pretty controversial because I dealt with some issues that some people held sacred. But the main point of the book is that water is absolutely central to all of biology. And those who have studied biology will know that water is not central to biology, that water is simply the background carrier of the more important molecules of life. And the book demonstrated that that was not so at all. And so the book was drawn from evidence from others because we hadn't studied water at all at the time. We were busy studying muscles and how muscles contract. So, of course, we became interested in pursuing experiments to determine more about the nature of that water, especially the water that's inside the cell, inside your cells. So we knew from the work of Gilbert Ling and many others that the water is something like this, that inside the cell is crowded with big molecules like proteins, and the proteins have charges on their surface, and next to these proteins are water molecules. And the water molecules are shown here simply as dipoles, which is a plus and minus. And you'd think it would be natural that next to one of these positive charges, you get negative, positive, and next to the negative ones, you get positive, negative, and they would tend to pile up, except that scientists know that there's something called thermal motion, that molecules are disturbed by this kind of motion. They tend to bounce around a lot. And so the going theory among chemists at the time was that next to these charged surfaces, you might perhaps have a couple of molecular layers of this stuff, which was kind of crystalline, well-ordered. But beyond that, disorder would reign, especially once you got to the third, fourth, or fifth molecular layer. And the evidence in the book at the time was that this could go well beyond that. It could even go to 10 or 15 or so molecular layers. But this was not clear, and the evidence was conflicting. So we wanted to study this kind of water because this kind of water was different from what's in the glass. And since water is everywhere and important, we wanted to find out. And so one of the characteristics of this kind of ordered water is that it's like a crystal, and crystals exclude particles and solutes when they form. So, for example, when ice forms, the ice pushes out all of the solids that aren't forming part of the crystal. So we looked for an experimental model in which we could see this kind of exclusion. And we found one, thanks to a Japanese colleague who alerted us. And it's actually quite simple. It's just you have a chamber, and in the chamber you put a gel, just like gelatin dessert. And that's shown here. And then you add to this water and little particles in the water. You just dump in the water plus the particles. And what you'll notice here, and what we noticed right away, is that there's a zone right here where the particles don't want to be. You see, and so we thought, aha, maybe conceivably, this could represent an area where the water molecules are ordered. And we didn't know, but we thought, but the situation actually is more dramatic than that, because over time what happens is that it's as though something is growing and pushing these microspheres out. Microspheres, little tiny spheres, particles that we use all the time. And once they're pushed out, they remain there essentially indefinitely. They undergo this thermal or Brownian motion, which you could see if I continued the video, but they never go back into this region. So it appeared that this microsphere-free or particle-free region was 50 micrometers or so, and that's close to the thickness of one of your hairs. It's pretty big by molecular standards. And so we grew interested in this, thinking that maybe this is our candidate. And it turns out it was, but we'll get to that in a minute. And someone said, well, you found something pretty interesting. You should give it a name. So what name do you give it? Well, my Australian friend suggested that since it excludes, why not call it exclusion zone? And so we called it exclusion zone, and the name has actually stuck. And it was a really good suggestion because the abbreviation for exclusion zone is EZ. Now, you say EZ, but we say EZ. So EZ is easy to remember. EZ has no such meaning. Anyway, we call it EZ. So we found soon that it wasn't just this particular gel that creates this exclusion zone, but we tried other substances. And this is another example. This is a polymer called naphthalene. So it comes in sheets, And you take the sheet and you cut it to whatever shape you like. You plunk it down at the bottom of the chamber, and you do the same thing. You add the microspheres, little particles, and water. And again, you can see this clear zone, the zone that excludes the microspheres, and over time, and we're talking about 5 minutes or so, over the 5 minutes, this is sped up, you get an exclusion zone, and in this case, the exclusion zone is so big, it's something like 400 or 500 micrometers, half a millimeter, that you can see it with your naked eye. This is taken through the microscope, but you don't need a microscope. You can just look and detect it. So we were rather astonished to find this, because lots of people have been studying systems like this, and nobody apparently had ever reported it. But we were wrong. Someone alerted us to a paper from 1970 where people were experimenting with the lens of the eye and also with contact lenses, and they found the same thing in both of them. Even the size was the same. But meanwhile, a lot of people have gotten interested in it, and this is a partial list. This was constructed about 3 or 4 years ago of people who have taken this up and confirmed. So we know that these exclusion zones exist. But the question is, what do they mean? Why are they interesting, and what do they tell us? So what I want to do is answer 5 questions. The first is this exclusion phenomenon general, or just those couple of slides that I showed? Does it really arise from the ordering of water? Because if it does, then we're talking about huge numbers of water molecules that can get ordered, which runs counter to most chemistry and physics that we know. Can water ordering explain those 3 slides that I showed earlier, which you had some ideas, but now to create order needs energy. And so if this is representative of some kind of order, where does the energy come from? Not obvious, but we found out. And finally, why should you be interested? What's the significance of all of this stuff for you? And it turns out to be rather central, I think. Okay, first question, generality. The answer is it's quite general. The surfaces on which these zones build, many gels that we've tried, polymers, surfaces from biology that we played with, and also monolayers. So what's a monolayer? It's a single molecular layer that you can implant on the surface of gold. And this creates very nice exclusion zones as well. So it's quite general. And then I should say, it's not completely general, because if the surface is so-called hydrophilic, water-loving, that's where you have a surface, you put some water and it spreads out. Then we find it regularly. If it's hydrophobic, like your Teflon pan, where you put the water on, it beads up, then we don't see this at all. So for hydrophilic surfaces is quite general. What's excluded from the exclusion zone? Well, we tried big particles, big molecules, and small molecules, and we found that the exclusion applies to substances whose molecular weight is about 100 or so, and maybe smaller. And I just want to give you one example of it. It's, you remember litmus paper in your chemistry? You stick the litmus paper and turns color, right? And so you can get the same chemicals that are in the litmus paper in powder form, and you put them in the water, and so, or in the acid or in the base, and it's the same result. It'll turn color based on the pH value. And these are substances that are typically molecular weight of about 100 or so. So a typical pH-sensitive dye will have a mixture of 5 of those different chemicals, roughly 100 or so molecular weight. So what we did is we took a chamber, we put a piece of naphthalene at the bottom, which creates a very nice exclusion zone, and then we poured the water and the pH-sensitive dye. And we wanted to see, since you can see the dye, you know where it is, we wanted to see if it's excluded from the exclusion zone. This is a rainbow similar to what you saw last night, but we saw it in the lab. But just pay attention to this. Here's the piece of naphthalene at the bottom. And you can see the pretty colors of the dye, but here there's no color. This is the exclusion zone that sits next to the naphion, and it's color-free, which means that the dye is not getting into it, which means that the dye, mixture of molecules, molecular weight 100 or so, are excluded from the exclusion zone. So this is just one example. But more important than that is the color distribution here. And the red color means a pH of 3 or less. And if you remember, low pH means that it's full of protons, right, like acidic. And so this is full of protons. This has fewer protons, and here this is about neutral here, roughly pH 7. So I'll get back to that in a moment. It's really important, but to summarize, the point number one, the question number one, is it general? And many hydrophilic surfaces generate exclusion zones, and many solutes are excluded. So it's general. Is the zone really physically different from, say, this kind of water? It's got water of some sort in it. We know that. And the answer is absolutely. And I'm going to list 8 pieces of evidence. I know of 10 pieces of evidence. I just want to keep it short. And I'm not going to go over every piece of evidence because we'll be here till midnight and you'll be really tired. And most of it's been published in case anybody's interested. So I'll just go through the list, and you can zone out if you like. But I feel obliged to present it because this is the heart of the evidence for what I'm talking about. So the first one is that the EZ water molecules are more constrained than ordinary water molecules, and we used nuclear magnetic resonance techniques to demonstrate. We found that the molecules are more stable. We found also that the EZ is not neutral. So, this stuff is neutral, but the EZ is negatively charged. And I'm going to show you that one because I think that one is pretty important. I'll come back to it. It absorbs light at a wavelength of 270 nanometers. That's in the ultraviolet. And ordinary water doesn't do that. So it's different. It's more viscous than ordinary water, kind of like honey, the same consistency of that. And the molecules there are aligned with one another. They're not random as exists here. And the molecular structure is different from this kind of water. And finally, the optical properties are different. And this came not from our lab, but actually from nearby here, from 2 Russian laboratories, actually both from Moscow. And these guys didn't know one another, but they did essentially in the same city, excuse me, the same city, the same experiment, one in a physical context and one in a biological context, and both found that the refractive index of this was up to 11%. They got the same number, 11% higher than that of water, which means it's more dense than ordinary water. So these are 8. There are actually 10 that I know of. So let's just go back to this one because it's particularly important. Because when you think of water, you think of neutrality. You don't think of negative charge. And the experiment is done as shown here. So what you see is inside and outside. Well, what does that mean? Well, inside means inside of a gel. So you put a gel here, and we used a polyacrylic acid gel. And outside is, well, obviously outside the gel, and that's water. So you have a gel and water. And you've seen that before in one of the early slides. And there'll be an exclusion zone that's roughly here. So we wanted to investigate the electrical nature of this exclusion zone, being really naive and just wondering whether we would find something interesting. So how do you do that? Well, you need 2 electrodes. And so we put one electrode out here, and that's the reference electrode. And we put a probe electrode right here. And the electrodes come and taper to a point that's very tiny. This is the same kind of electrode that's used by many people, including us, to stick into cells and measure the electrical potential without killing the cell. Okay, so if you put the electrode here, then what this shows is that the potential difference between here and the reference electrode out here is 0. Now that makes sense because basically, you're just putting 2 electrodes into ordinary water far from any interface or anything, and you should get 0. So that's reassuring. The surprise came when we brought this closer and closer to the exclusion zone. And the exclusion zone for this gel is roughly a couple of hundred micrometers here. So as you penetrate into the exclusion zone, you pick up a negative electrical potential, which went down to about minus 120 millivolts. We were surprised because it looked like this is negatively charged. And so we decided to try another specimen, and we pulled out the gel from here, and we put Nafion instead, and we repeated the experiment. And here's the result with the Nafion. And you can see that qualitatively, it's pretty much the same, but quantitatively, you can see that the negativity begins farther from the interface, and it gets more negative. It goes all the way down here. Well, it kind of makes sense because, as I mentioned, the exclusion zone for Nafion is much bigger than for this particular gel. So it looks from this result, it looks as though the exclusion zone has negative electrical potential. And at first we were shocked by this. We couldn't believe it. And there was a Russian guy, a friend of mine, who was working in the laboratory, and he immediately telephoned his wife, who was in Russia, and she was using these microelectrodes, and they were playing with gels. He said, "Please repeat this experiment." She did, and the next day, the same result. So we're quite sure of this result. However, it doesn't make any sense. If you think about it, so we took a gel, right, and we added water. We poured water in the chamber. This water is neutral. So how is it possible that you can pour neutral water into the chamber and get all of this negative charge? You can't get the charge from nowhere. It's got to come from somewhere. So after scratching our heads for a while, we thought the only conceivable way that this could happen is if the water molecules, that are here, are splitting into negative and positive components. Negative component is OH minus, and the positive is H plus, or the protons. So then we said, well, gee, is there any evidence for some positive charges? If we got the negatives here, should be positives there, and is there any evidence for the positives? And the answer is you've already seen the evidence. Remember the pretty rainbow colored? I turned it 90 degrees now to match the format of the previous slide. So here's the Nafion. The microelectrodes showed negative electrical potential in the exclusion zone. But remember, the dye showed lots of positive charge here. So it does look from this as though somehow the neutral water is splitting into a negative and a positive. Well, just to make sure we weren't deluding ourselves into thinking that there's something there when maybe there's nothing, we stuck 2 electrodes in, one in the negative region, one in the positive region. We connected them through a resistor. And if there really is separation of charge, you should get current going from the plus to the minus. That's what we got. Current versus time. So it starts at some high level, relatively high, and it goes down and it falls down to a plateau. And that plateau is not 0, here's 0. So there's steady current that keeps flowing from the positive region to the negative region, which means that there must be a separation of charge. See, so it means that it confirms what we had suspected. And so basically what we've got is a charged battery in water. You see, we have some kind of hydrophilic nucleating surface next to water, creating an exclusion zone that's negative, and ordinary water that's full of protons, minus and plus, out of which you can imagine this is a battery you can get energy. And I'll show you at the end that we actually can get energy, electrical energy from this. Okay, so going back here, EZ has negative charge. That's the point that I wanted to make. Okay, so now with all these properties, you may ask the question, what kind of structure is this exclusion zone? And I gave you a hint before about the lining up of water molecules. If you, if you look at these three properties in blue, the molecules are aligned with one another, and they're stable and constrained. And this is characteristic of a liquid crystal, kind of like a screen on your laptop computer. I'll go into it a bit more because this is kind of vague, and I want to draw some specific conclusions out of that. But just so far, to summarize, we have next to a hydrophilic surface, if we have water, the water is some kind of liquid crystal, that is some kind of ordered entity, and it has negative charge, and it excludes solutes profoundly. Nothing will go in here, essentially. Based on the list of properties, we might not be right in presuming that these are dipoles that are stacked. I'll get back to that in a moment. And it may extend very far from the surface. So how far is very far? Well, the textbook, the chemistry textbook, said maybe 2 or 3 molecular layers at most. And experiments that we've done suggest that instead of 2 or 3 molecular layers, it might be 2 or 3 million molecular layers. So it's a huge difference between what is accepted right now and what the experiments seem to show. 100 years ago, Sir William Hardy, a famous physical chemist and colloid chemist, said, there's a problem. He said, everybody knows that there are 3 phases of water, solid, liquid, and vapor. We all learned that as school children. However, if you start with these 3 phases, you simply can't explain all there is to understand about water. There are many features that don't fit into this paradigm, and so he suggested there actually might be a 4th phase of water somewhere in between a solid and a liquid. I think that's what we found, although I'm not sure. And so this kind of water that experimentally we've demonstrated, which is a lot different from this, could be that 4th phase that was predicted more than 100 years ago. Okay, now, what about non-dipolar? These dipoles are pretty simple to understand, and they make a lot of sense. And I even had a picture of them in my 2001 book, so it's a little embarrassing to suggest that there might be something wrong with that picture. Well, other people have had similar pictures. So why, such a simple kind of observation, why would anybody want to challenge it? Well, the reason is it doesn't fit the evidence, and it's actually not very complicated. We found that the exclusion zone has a negative charge, but dipoles are neutral. A dipole is a plus and a minus, which sum together give you 0. So you can stack dipoles from here to the moon, and you'll never get a negative charge. It's always neutral. And there's another piece of evidence that maybe is less important, but this kind of absorption of ultraviolet light is not characteristic of dipoles. Usually it's ring-like structures that are responsible. So mainly for this reason, we have to reject this model. So if that's wrong, what's right? We stood in this kind of precarious position in trying to figure out what might be the structure. And it's not so simple to do, but we took a simple route. So we said the first option for a kind of structure would be something that's similar as precedent to some other water structure that we know for sure. So what water structure do we know for sure? Liquid water? No way. Great debates about what is the structure of this liquid water. Vapor? We think of vapor as single molecules floating in the air, but the evidence written in my recent book is certainly not, that's not the case. But ice, so, ice is a crystal, and crystals can be studied by physical chemical techniques, and the structure of ice is very well known, so ordinary ice. So we thought maybe one possibility is that this structure that for the exclusion zone could be some kind of variant on ice. And we thought that made sense, at least as a try. So what's the structure of ice? It's pretty structure. We've seen in the last talk hexagons, and you can see the hexagonal motif showing here. So this is ice. It looked on at this from this particular angle. It shows it's a honeycomb kind of structure built of hexagons. Okay, and it's stacks of honeycomb sheets. If you look at, by the way, these red spheres are oxygens, and there's hydrogen too, but they're just omitted to keep it simple, to keep the clarity. I'll show you them later, but they would exist halfway between each pair of oxygens. So now, instead of looking from almost directly above, if you look from some angle, then you begin to lose the sense of hexagonality. It's the same structure, just different angle. But then you pick up these blue dots that you see here. So what are the blue dots? Blue dots are protons, positive charges. And so what they do is you can see that you have the negative oxygens here, and they're held together by the positive proton. So it acts like glue. And that's why ice is hard, because you've got the glue in between. So we thought, okay, starting with this structure, is there any way that we can modify this structure to conform to the characteristics that we need for the exclusion zone? So we thought, aha, we're clever. Let's do this. Let's remove these protons, right? And so by removing the protons, you convert a structure that's neutral. If you take away the positives, then you get something that's negative. Well, the experiments demand negativity here. So we thought, this is going in the right direction. We have negative charge, and because we've removed the glue, then it's not solid anymore, and the exclusion zone is more gel-like than solid. So we thought we were on the right track. We thought, until a friend said, it's a good try, but there's one minor problem, and that is it's impossible. Okay, thank you very much. Why is it impossible? Well, actually, it turns out it's a very simple reason, because if you take away the positive charge from here, then you've got two negatives sitting right next to each other, and negatives repel each other, and therefore, if you remove all the blue dots, these layers will just fly apart because of these repulsive forces, so it doesn't work. So after a few weeks of depression, similar to what people feel in Helsinki in the winter, I think, finally an idea came. And actually, it came on a trip back from Japan, sitting in the, oh, yeah, this is, and so it's very simple, and I think it solves the problem and actually works. And that is, if you take the two layers, or the multiple layers, if you take two adjacent layers and just shift one by half of the repeat distance, just this way, then everything works out, because you can see it, whoops, you can see it here. So you have one layer closer to you and the other layer farther from you. If you take the closer one and then shift it by a distance equal to, well, half of the oxygen distance, then everything lines up really nicely, because you have an oxygen, negative oxygen behind, positive hydrogen in front. One's positive, one's negative, and they stick. They stick not like ice, but weakly. You see, so at least the structure is stable, because all the layers stick to one another. See, it's not rigid, but it's more sort of gel-like. But we solved the sticky problem. And this still has negative charge that we need, because we pulled those blue protons out. Well, they might have different colors, but who knows. Okay, so then we have something that seems to work. We have a hydrophilic material, a nucleating material, that takes the water sitting next to it and converts the water layer by layer into these EZ layers. And so, you got 4 of them here, and a 5th one, and a 6th one, and they just keep building from the water. They build from the water. And if you look at the molecular structure of this, it looks something like this. And here we've restored the hydrogens where they belong. And you see the hexagonal structure. And if you try to figure out, well, what's the chemical formula of one of these unit cells, it turns out it's not H2O, it's actually H3O2. And that's just by counting. And it makes sense because this is negatively charged, right? For something that's neutral, it would be neutral as H2O or H4O2. This is H3O2, so it's kind of missing a positive charge, and therefore it's net negative, which is what we require. In order to get this, if you remember a couple slides back, I just shifted one layer to the right relative to the layer behind it. And it was very nice because the negative and positive line up, and so you get a kind of stickiness out of that. But I didn't have to shift it to the right. I could have shifted it to the left, or I could have shifted it 60 degrees or 120 degrees because it's entirely symmetrical. And why is that interesting? Well, it's interesting because it's versatile enough to build interesting structures. So this is a helix that you see here. And I got it by taking layer 0, and taking layer 1 and shifting it by 0 degrees, 60 degrees, 120 degrees, and I obtained a helix. So what's the big deal about a helix? Why is that important? In biology, everything is helical. Well, I shouldn't say everything. Many things are helical. DNA, RNA, fibrous proteins. Biology loves helices. It's also known that next to each one of these structures is some kind of ordered water. So this model has the versatility to create a helix that could fit right next to a helix, for example, of DNA or a fibrous protein. And that, I think, is an advantage of this particular structure. So just to summarize the advantages, one, it's precedent. It's not ice, but it's kind of similar to ice. So it's a known structure. It comes from something we know. It's not just a rabbit pulled out of the hat. It's got negative charge, which the experimental results demand. The ring-like structures might explain that absorption in the ultraviolet. It's able to accommodate helical structures. And this crystal-like structure can actually be, you'd expect that it could be, under the right conditions, it could be solidified because crystals can be solid. And a very nice experiment was done by an Italian group, Vittorio Elia, and he took EZ. He took some Nafion and he scraped the EZ off and put it in a beaker. He let it build up again. He scraped the EZ, put it in the beaker. Actually, his wife did it. Again, the women. She's much more competent, he admits. And so he does this many times, scraping off the EZ water. Then he takes the EZ water and puts it in a device called a lyophilizer, which pulls off all the loose water. And what's left is a solid at the bottom of a flask. And you can just scrape off the solid and feel it. And he gave us some of that. We brought it back to our laboratory. It's a kind of fragile string-like material. But think about it. This is a solid water at room temperature. Solid water at room temperature. And it's EZ water. And so the fact that it can be a solid is interesting in terms of information and memory. And let me just say a few words about that. So we have a structure that we believe the best evidence is that it looks something like this. And you have a nucleator that is a hydrophilic surface. We call it nucleator because it nucleates the growth of these EZ layers. And the question is, well, is this amenable to the storage of information or containment of memory? Most people would think that this kind of water, that it's impossible to store any information because if the molecules are bouncing around randomly many times per microsecond, how could it store information? However, if you have this kind of water, then it's different because it's semi-solid. That is, all the atoms inside are connected to one another. And so if you think about information, how possibly would this store information? There are two ways that we can think of. The first is that the nucleating surface, or nucleator, on its surface it has a distribution of charges. And this distribution of charges can affect this entire lattice. Let me explain that. So this is the nucleating surface. And if you have a kind of generic surface, let's say it's plus, minus, plus, minus, plus, minus, boring, nothing unusual, well, there's probably no surface like that, but it's just for illustrative purposes, then this will nucleate the growth, this is the surface I just showed you of this, of exclusion zone layers, but there's no real information in these. However, if you can imagine now a real surface, real nucleating surface, where there are some, shall we say, defects or differences. For example, this yellow could be another plus. See, so again, you disturb the paradigm of minus, plus by having some differences. And so then when the water piles up next to it, the next layer is going to show comparable differences from the information from that nucleating surface. And those defects can project over many layers, and therefore, basically, you have an array, an easy water array, a kind of semi-solid that has information, that has these, it's not regular as you see here, it's different, and that difference is information. So that's one way of imparting information. A more interesting way, by the way, I should say that probably the water inside your cells, which is mostly this kind of water, has this kind of information. Probably the proteins in your, for example, in your muscle cells have certain charge distributions, and that confers a kind of novelty or speciality of the water in your muscle cells, and your liver cells will be different, and so on. So this is a kind of generic structure, but there can be defects or differences in this generic structure that mean information. Now, the more interesting way of imparting information is through electromagnetic information. So you can imagine we have electromagnetic energy coming into the water, and presumably there's some degree of easy water that sits in here, and it sets up, there are resonant vibratory modes according to the frequency of the water that comes in, which may affect, again, this region or this region or this region, and these regions will then change based on the information that comes in, and this could be retained over a long period of time. And not only that, but because of these vibratory modes that differ from all of the others, this is also generating information, so this water can then give information out. Also, it can impart the information that it has to other entities, you see. So it's possible that input electromagnetic energy, which could include just standard light, for example, or it could include perhaps prayer. We're all radiating energy of some sort, or intent, or something like that. There is the capacity to store information, at least theoretically. And that can happen. And this can actually happen in each one of these oxygens that you see here. See, these oxygens that are sitting have 5 different oxidation states. We've learned that, you know, oxygen can be -2, its valence, but actually it's more interesting than that, because each oxygen could be -2, -1, 0, even +1 and +2. See, so each one has 5 different states. So you can imagine the amount of information that could be stored in each one of these. So you think of, let's say, this guy sitting right here. It could be -2, -1, 0, +1, or +2. And the same thing for each one of these here. And the amount of information that can be stored is absolutely enormous. Especially compared, for example, to a digital computer memory, which also has arrays, regular arrays, just like these, and each entity in the array, each silicon or silicon dioxide, can be -0 or 1. That's how digital computers work. But here, instead of 0 and 1, we could have -2, -1, 0, +1, and +2. So this is an interesting potentially a powerful source of information storage just in the water. See? And And so what's not known is exactly how this works, but somehow electromagnetic waves can impact, let's say, this one and this one and this one, depending on the frequency and the wavelength. And we don't know how yet. And this is now under study, including under study in our laboratory. So I just point out that because this is a semi-solid, it has, and a regular crystal, it has huge information storage capacity. And I guess maybe it's possible sometime in the future, as computers get smaller and smaller, that one day information storage in EZ water could conceivably replace what's now in a digital computer, and they may get smaller. Okay, the answer to question 2, this is a long one, I'm sorry, is the EZ, that was the question, is it physically distinct from the bulk? And yes, I listed 8 different properties and the best information we have is that it's a layered honeycomb structure. That might be wrong. You know, we feel confident, or we as scientists usually like our own models, but then, you know, it just takes, to destroy one beautiful theory, it requires only one ugly fact. And so we're quite prepared to be wrong. Question 3, okay, if the water is this regular crystalline water, then can that explain the first few slides and even beyond that? Those counterintuitive kinds of things about water. Well, what kind of behavior do we expect from a crystal of water? Well, some of you have played with crystals, like a sugar crystal or a salt crystal. You know, they stick together. They basically stick. All the layers stick to one another. And so crystalline elements stick together. Excuse me. And that comes to the dessert that you may or may not have enjoyed last night, Jello. We have a gelatin dessert. So what's gelatin dessert? It's 95% water. Those of you who've made it know that. It's mostly water. See, and so a question that you may or may not have asked is, if it's almost water, how come you can't pick up, how come the water doesn't just dribble out of the gel? Maybe you never asked that question. I'm not sure. What keeps all that water in the gel? I handled gels some years ago when I was in Japan, and I went to a laboratory in Hokkaido, and they were producing gels that were not 95% water, but 99.95% water. It's essentially all water with a few strands of polymer. And the question is, how is it possible that all that water could stick without dribbling out? And so this is a kind of, you know, question you may think about, and I'll come to a suggestion in a moment. This is what gels look like. So the gel consists of a matrix, which is shown here in the yellow, and it's got spaces in between, these large gaping holes in between, and that's where the liquid is, that's where the water is. And so question is, you know, how come there's all this water and all these holes are interconnected? Why doesn't it just come out? And I think the answer, chemists would say that it has something to do with osmotic forces that pull the water, but when you have a case where the water is 99.95% water, just a tiny amount of this yellow stuff, it's hard to comprehend that would be the case. But there's another interpretation, and that is these are hydrophilic surfaces. And if you've been listening, if you remember the evidence, if you put water next to a hydrophilic surface, you get easy layers that start building up. So most of this water that sits here is not H2O sitting here, it's actually EZ water. And that's the reason it sticks, because the EZ layers stick to each other and stick to the nucleating surface right here. So I think that's the reason why the water doesn't dribble out. And if you think about it, some of you maybe have asked the question of gels, you know, they have this kind of weird consistency. Okay, and so I think the reason gels are gel-like is because the EZ water that fills the gel has this kind of consistency. Okay. So then another question. Some of you have seen this before or tried it. You have a glass of water, and you put a pin on the surface or a paper clip, and it doesn't sink to the bottom if you do it carefully. And the question is, well, how come? If you put it beneath the surface, then it sinks to the bottom. So what's going on? And the usual response is, well, yeah, water has a high surface tension, and that's what keeps it up. So what is this high surface? I think I'll skip that. Let me just go on. We found that the reason, we think, is that at the interface, right up here between the liquid and the air, there's a thick zone that's EZ water, which has a gel-like property. And we think that that's what keeps it up. And the experiment is shown here. So the experiment is you take 2 sheets of glass and you then seal it at the edges. And you put in water and microspheres. And that's why it looks cloudy here. So you have air, then you have a meniscus. And we found that although these microspheres in water go all the way up to here to start with, a clear zone forms in about 15 to 30 minutes, and it stays that way. And so this looks like an exclusion zone, just similar to what I've shown you before. And we found that it has negative charge using microelectrodes. And the next slide will show you that this is not just water, this is a gel-like band that exists there. So this is, the video will show that to you. This is exactly what you saw previously. And then we have a rod, and the rod is going to hit the surface. And you'll see that despite the mechanical disturbance or perturbation, the thickness of this doesn't change hardly at all. So we're coming down now, we're lifting up, and you can see the height of that dark region. It doesn't change, which means that it's cohesive, which means the molecules inside here are sticking together just like a gel. And so we think this is the reason why you can take dense substances, and if you do it gently and carefully enough, this is an old Hungarian coin, by the way, it floats. It's because you have many structured layers that create the high surface tension. And that explains what I always like to show because it's so cute. This is a lizard from Central America, and it sits on the branch. And when it gets the urge, it jumps off from the branch and jumps into the water. And it walks on the water. And so because it walks on the water, it's called a Jesus Christ lizard, because it walks on the water. And I think the explanation for that is, as I showed you, because the top layer of water has this structure to it. And that also explains what happens. Remember the second or third slide, we dropped water on water. But it's not dropping water on water. It's water that has an EZ layer right at the top. And also, this has a similar EZ layer here because the water is exposed to the air, same as here. And so it forms an EZ layer out here. So when you drop this on this, the reason it doesn't coalesce instantly is it's not water meeting water. It's EZ meeting EZ. And the dynamics of those are perhaps difficult to predict, but this is what happens. It floats for a bit, and then boom, it does that. And it takes about 6 steps to dissolve completely. This is not new this has been known for 100 years. We just had a new high-speed camera, and so we thought we'd take some pictures.
That's a fascinating picture, by the way.
Oh.
Getting smaller and smaller, I had no idea.
Yeah, this is the way, that's what it does, and it, of course, requires interpretation. But the coalescence is not instant. Okay. Now, another point about crystals is that crystals can be pretty stiff. Some of you have diamonds, rubies, whatever. So then, if we apply that principle that crystals can, even salt crystals or sugar crystals, what you got here, so this is a very stiff structure. You can test the stiffness or you can assess the stiffness just from the length, the amount of droop, and the diameter. You can calculate. This is so stiff that it looks as though you can practically walk across this bridge. Water doesn't do that. This stuff, out of this, you can't get this. But if you have EZ water, crystalline water, then you can. And so I think that's the explanation for this. And finally, in this series, most important is something that those of you who are scientifically oriented may have noticed and felt uneasy about. You have a negative region next to a positive region. Usually the two come together and annihilate one another because they attract each other. This doesn't happen here. If we stick one electrode here and one electrode here, the electrical potential difference remains indefinitely. So it means they're kept apart. How is it possible that they're kept apart? Well, these positive charges here, which are actually not protons, they're protons stuck to water to give you a so-called hydronium ion, they want to penetrate in here. And I think the reason they can't penetrate into here is because of this grid-like structure. You know, if they want to go into this region, they have to pass through a hexagon. The hexagon is pretty small, but the next hexagon is shifted, and which effectively makes the tunnel even smaller. You see, so it's very difficult for physical reasons for it to penetrate all the way into here, and so therefore the battery charge remains separated, which is what we observe. So the answer to question 3 is, yeah, liquid crystalline water explains many anomalies, and it explains why the water battery charges remain separated. Okay, so now here's question 4. The critical question, what charges this battery? Every battery needs to be charged. Your cell phone battery, you need to plug it in to recharge. And we couldn't figure out the answer. Finally, a student, an undergraduate student, young undergraduate, did a chance experiment that showed us the answer, which is light. Light is what's responsible. The energy from light is responsible for building this. And so the experiment is, we had a chamber that was sitting right here, and we got a lamp. He has a lamp. He took the lamp and shined it on the chamber. And here's what we saw. So this is Naphion. Schematically, here's the lamp that he put. And in the exclusion zone and microspheres, in the region where he illuminated, you can see the exclusion zone is growing like this. And so it didn't take a rocket scientist to figure out that, you know, you turn on the light, it gets bigger. That light seems to be building up and driving this. So, of course, we did many experiments with different wavelengths. I won't bore you with that. But what we found is that the most powerful light of all is infrared light. So you may ask, you know, where does infrared come from? Where do you get it? Well, you know, if you look in your toaster, it glows red, and you know infrared light is coming from there, and the same with an electric range. But actually, it comes from everywhere. If we were to turn off all the lights in this auditorium, so you couldn't see anything, and I take out my infrared camera and turn it on, I get a beautiful image of all of you, of the chairs, of the camera, of your HP computer. And the reason I'm getting that is this camera is sensitive to infrared is because everything is generating infrared. You can't get rid of it. It's there, or it's very difficult to get rid of it. It's actually free energy in the literal sense. It's free. It comes, you got it, you don't have to pay for it. And that's the energy that's building this kind of fourth phase of water. Therefore, because it's there, it's free, you always have fourth phase water around everywhere. So, yeah, it's coming from everywhere. So if you have some hydrophilic material next to water, it'll build the ambient infrared is going to build this EZ water. And if you add more, then the EZ will grow bigger. And if you take it away, it'll grow smaller. So it's always there. And the answer to question 4 about the energy is the EZ buildup is powered by light. And the light orders the water and charges the water battery. So the situation is like this. And you just, the battery just lies in the sun and gets its energy. Now, if you think about the implications of this, they actually are quite profound. And so if you think about the energy flow in the universe, or at least on the Earth, so we know that the sun hits the water and generates heat, so you can go swimming in the summertime. What I've shown you is a different pathway. I've shown you that the sun hits the water and imparts energy for building order, building the EZ, and separating charge. So now, if that's true, if what I've told you, it means, no, this water is receiving energy all the time from the environment. And if that's correct, and it's building EZ, right, is it possible for you to collect this energy somehow? Now, my guess is that not one of you has ever seen a glass of water doing work, right? And tell me if you've, well, I'm going to show you that water can do work. And this, again, was a chance observation made by an undergraduate student. And so he came in the lab, and we discussed a project, and his project involved using these tubes of naphthalene. It's just like a straw, but it's built of naphthalene, which gives exclusion zones. And I don't remember what we agreed that he was going to do, but one day he came running into my office. Someone else was there. He just barged in, and he said, "I got to tell you what I saw." And I understand his excitement. What he saw, what he told me, is that he had this water, and it had some particles in it, so he could see what was going on in the water. And the microscope was down here, the microscope lens looking in. And he said, whoops, oh my goodness. He said the water flows continuously through the tube, like through a straw. And so this may not seem earth-shaking to any of you. I mean, it flowed continuously, but it was to me because I know that when you have a tube like your arteries, you need your heart to pump the blood through. You need pressure to push water or push any liquid through a tube because the water has viscosity to it. And I thought, there's no pressure here. It's just sitting idly at the bottom of the chamber. So I thought, this is really interesting evidence that the energy must be coming from the absorption of light energy into the water. And I thought, this is really cool. So, of course, we checked to see that this was real and such. And the experiment looks like this. You pick up the tube, and you insert water, make sure there are no air bubbles in the tube, and then you insert it into the water, which has some particles in it. Look in the microscope, and here's what you see. Here's the naphthalene, and here's the exclusion zone, and all the microspheres are here, and the microspheres in water are flowing through the tube. We had it going. We have had this going for as much as a day and a half. We thought, maybe this is something weird about naphthalene, so we tried to find some other tubes of other hydrophilic material. We couldn't, so we made our own tube, and we made it from a gel. You know, the way to do it is you have a gel that's first a liquid, and gradually it gels. You put a wire in it, and as it gels, you pull the wire out, and so you have a chunk of gel with a tunnel that runs through it. And then you take this, put it in water and the microspheres, and so this is what you see. This is the gel. Here's the exclusion zone that sits next to the gel, exclusion zone. All the particles get pushed right to the center, and the video shows that same thing. We've tried at least a half dozen gels, the same result every time, except the speed may be different. And someone said, if you think that the energy for driving this flow comes from light, why don't you just give more light and see what happens. And we did the experiment without details. I can tell you that we were able to, we just published the paper last year, to increase the speed by a factor of 5 times just by increasing the light. So essentially we have a hollow tube. Work is done because, to move water through a tube, that's work because the water has viscosity to it. And to do work, you need energy because there's no such thing as a perpetual motion machine. And so the energy, as I've demonstrated, is coming from the environment, and this energy absorption is a necessary condition in order to keep it going. And so from that, we conclude that water actually is transducing light energy into mechanical energy. So in other words, the light that's being absorbed by the water is getting transduced and turned into mechanical energy. So this is actually doing work. It seems to border on the absurd. However, that the water is a transducer. But just think about the plant that sits on your windowsill. So where does it get its energy? Well, it gets its energy, obviously, from light. And the light is absorbed. It builds chemical energy, chemical potential, and that turns into all the things that the plant does, from metabolism to flow to growth to bending and all of that. And so the experiments are implying that the very same thing happens with the water, that the water is absorbing the light energy and transducing it pretty much as the plant does into other kinds of energy. And it shouldn't be a surprise because the plant is mostly water. So it's not really that strange after all. So we come to this equation that is similar to the iconic equation that's been discussed before, but this is what I mean to say, even though I understand the units don't match, is that water is actually full of energy. It's not devoid of energy. It contains energy. Okay, finally, why is all this important? Well, I think it's foundational for any or all science involving water and molecules and light. So here I summarize what I've told you during the past hour, and that is you take a charged particle or molecule and put it in water, and it builds this big exclusion zone, which generally has negative charge, and the complementary positive charge is sitting out here in the water. And all of this is powered by light. And so if all I've demonstrated to you is true, again, you know, we never know. If all of this is true, it basically applies in all aqueous chemical reactions. And so if you go back to your chemistry textbook, those of you who have studied chemistry, and look at the reactions and see how the reactions are interpreted in the chemistry book, there's none of this that appears in the chemistry book. So it means that many of the interpretations, if we're right, will require revision. And so and one example is of this is a phenomenon of what happens if you take two of these and put it in water, let's say two negatively charged particles. Okay, so I've got the water here, and I take two of these particles and I drop them in the water. They fall near each other, so they feel one another's charge. They're both negatively charged. So I ask you, some of you know the answer, so what happens to the distance between them? Does it increase or decrease? They both have negative charge. Is there a repulsive force? Or yeah, and so they should move apart from one another, right? Okay, the answer is that they come together. And this is a paradox known for 100 years, discussed by some of the most famous chemists and physicists as to what's going on here. It shouldn't do that, but actually it's doing it. And the great physicist Richard Feynman discusses this phenomenon, the paragraph, he calls it like likes like. So what does that mean? Well, these are like charges, and they like each other, so they come together, right? Okay. So, I mean, in his own inimitable way and sense of humor. And he said, like likes like because of an intermediate of unlike. So that means if these are negative, you have an intermediate of positives. So, this is a very, very reasonable idea, but until recently, it wasn't clear where these positives come from. So I've demonstrated to you where they come from. As this negative builds, you get the equivalent positives out here from the splitting of water. And you got a lot of them here because you get contributions from this one and from this one. So these positive charges are simply attracting the negative charges, and there's no violation of any physics. It's just that you happen to get opposite charges in between. So like likes like because of an intermediate of unlike. This is an extremely important principle that is underappreciated, extremely important. And it actually it comes from the ancient Japanese literature. Some of you may know the tale of Genji, about families, parties that are at war with one another, and the idea is that they will never come together unless the appropriate attractor is placed in between. So like likes like because of an intermediate of unlike. So same thing happens, they come together, and when do they stop? Well, you get stability when the attractive force, this pulling this and this, is equal to the repulsive force, the repulsion here. And there are lots of experiments that demonstrate it. It's been this has been known now for many years. We did some experiments ourselves with similar results, but it's not original at all. So if you have, instead of 2 of these, if you have many of them, then this is called a colloid crystal. And colloid crystals are well known and well understood. And according especially to Norio Issa, a famous Japanese scientist, it's very simple that you have these colloidal particles with negative charge, and you've got the positive charges in between that bring them together. And so if you've had yogurt today, probably the consistency of the yogurt derives from this kind of paradigm, because the colloidal particles in there are negatively charged milk particles. So they stick together because of like likes like. This is basically a self-assembly principle. You don't need anything to bring stuff together. So in this case, in the colloid crystal, you have a beaker of water, and you put some particles in, and the particles come together, and they actually form regular arrays in various regions in here, leaving voids in between. So clusters of ordered particles, things come together. And I think this principle is terribly important in biology, where molecules are actually created, but nobody knows they're assembled into rods and spheres and such. And this is a possible explanation. And when you think about the origin of life, of course, none of us have been there, so this is pure speculation. But you can imagine that there was a primitive Earth, there was water, there was sun, and some molecules of some sort, nobody knows. But you can't create a cell or something unless those molecules are drawn together. This like principle can draw them together very simply. So it almost is as though step 1 in the origin of life is inevitable, and maybe the beginnings of life are being created right out there, right now. And so you get to the cloud then, and we return to this question of how come you may get one cloud when the water is evaporating all over. And the answer, I think, comes from the like principle. So if you look at this cloud, it consists of these negatively charged aerosol droplets. Now, if you think about negatively charged droplets, you know that they'll never come together because they repel each other, but they don't. All you need is positive charge in between, and the atmosphere is full of positive charge, brings them together to form a cloud. Okay, does biology use radiant energy? This is kind of surprise result, or maybe hypothesis is better. So you're Mother Nature, okay, and you've already invented single-cell organisms and green plants, and they all use light, right? And now you create animals. And so Mother Nature, what do? Do you throw away the exploitation of light that's absorbed, or do you maybe keep it in reserve and use it? So most of us have learned and thought that we don't use light really in any important way. And the suggestion that comes is maybe we do. Maybe Mother Nature, in her wisdom, has actually designed us in a certain way to actually use the light. And so there are several different ways that one can think of, and the simplest one is the cardiovascular system. So you would never think that we use light in any way in our circulation. I didn't think so either. I did my PhD thesis on the hemodynamics, blood flow, cardiovascular system, and I thought we had it all worked out. Until about 8 years ago, when I visited my colleagues in Moscow, and my friend introduced me to the guy next door in the laboratory. He wanted to let me know what this guy thinks about circulation. And the guy said, we have a big problem. So, okay, what's the big problem? The big problem is in the capillaries. So in a healthy young adult, capillary diameter is 3 or 4 micrometers, pretty small. But the red blood cells that need to pass through that are twice the diameter. They're 6 or 7 micrometers. So he said, you got a plumbing problem there. It's like, you have a tube. It's kind of like a toilet, where you have it's a bit narrow, and the stuff that needs to get flushed down the toilet can't quite make it. And so you have to push, you have to plunge it. Some of you have had that experience. It's a similar problem. Nature, it seems that nature maybe made a mistake and designed these vessels to be too small. But somehow, there's a lot of energy that needs to be imparted in order to get it through. So they calculated if the heart is responsible, certainly the heart's responsible for pushing the blood through the big vessels, but when you get down to the small vessels, they calculated that if the heart is responsible, it would need to generate something like 1 million times the pressure. Even if they're wrong by 1 or 2 orders of magnitude, something is really awry. So it would appear, if they're right, and I think they're right, that the heart needs some assist. So where can the assist come from? Well, a possibility is light that comes in. The capillaries are not so deep, and actually light penetrates pretty far. Some of you have had the experience. You get into a closet, you dark adapt for 10 minutes, you turn on the flashlight, and you can actually see the light coming through the palm of your hand, which means that the light can penetrate pretty deeply into us. Different wavelengths, different amounts. So you have a situation like this. These are capillaries that you see here, and these are the red cells. And the red cells should look like this, but actually they're squashed as they go through. And if you look at the video, you can see that they remain, they have to be compressed in order to get through, and this guy is having a hard time working his way through. And so the question is it possible that in these really small vessels, which require a lot of energy to push the red blood cells through, that light, absorbed light, plays a role in driving this? And I wouldn't suggest that if I hadn't shown you this result where we simply have a hollow tube and we have energy coming in, basically light energy, and that light energy is driving the blood that goes through. And so we have the same thing in us. And so the question is, might radiant energy help drive the flow through your capillaries? And there's a graduate student in my lab is working on this, but there's one enticing piece of evidence from the literature. An Israeli research team was investigating blood flow in capillaries in mice. They used a rather fancy device. It's called, the method is optical coherence tomography. It's a big, long name, but all it means is that you have a device, and if you, for example, put it next to my cheek, it generates light, and the light is scattered, it comes back, and they can image the capillaries that are pretty deep inside. So this group used this technique to look and measure blood flow. And their experiments had nothing to do with what I'm talking about, but after they finished their experiments, as is typical, they sacrificed the mouse. But they kept the measurement device in place, and they found that after the mouse died, so the mouse died in 1 minute, the blood kept flowing after that. And they were looking at it, and they saw that it kept flowing for as much as 5 minutes, 10 minutes, 30 minutes, 1 hour. And they thought, this must be a super mouse. So they tried 10 other mice, and still it was flowing in all of them at least 1 hour. So it means the heart has stopped. There's something else that's driving the flow. I mean, this is pretty clear and obvious. And, a possibility is that the device, in order for this device to work, it imparts light. So it's putting light through the capillaries, and it's possible that that light is really what was driving the capillary flow, and that's why the capillary flow just kept going, see? So it's not only that, but all of our cells receive radiant energy, and the cells, as I intimated, are filled with EZ water. See, and actual cells, these molecules in the cells are packed really tightly, and therefore, whatever water there is, most of it is going to be easy water because it's interfacial. It sits right next to these, and there are so many of these sitting in the cell. And so I'll just make a point now, especially in Helsinki, that you asked the question, you know, if you suddenly it's in the middle of winter, somehow you go out and you see bright sun, it feels good. Or if you actually go into a sauna for 20 minutes, as I experienced last time I was in Finland, I went into the sauna and I was tired and achy and just itching to go to sleep. And after 20 minutes, it felt like everything was renewed. It's wonderful. So what's the mechanism? Well, I think the mechanism actually has something to do with the water in the cells, because the cells need easy water in order to perform. If we're deficient, as people with gray hair tend to be deficient, we add infrared light. Infrared light builds easy water. And so what happens if you go into the sauna, you receive the infrared heat, and this restores you, and it restores essentially every cell in your body. So whatever is your problem will have a tendency to get restored, enhances our health. So I'm not suggesting that we as humans photosynthesize, but I am suggesting that we do use light in ways I think that are unexpected. And this is very important. There's a lot more to say, but obviously I don't have a lot of time to say it. So I just end with two practical applications, if the other stuff is impractical. And that is, the first one is getting energy from sunlight and water. So I told you about the easy water having negative charge and positive charge beyond. And you can imagine sticking one electrode here and one electrode here. It's like a battery. It should light a light bulb. And this is an experiment that shows it. So these are a bunch of these little cells with naphion in them and electrodes. And when you turn on the switch, it lights the light. So we actually can get electrical energy out of water and light. And this has some future, we think, because you know, the current photovoltaic cells basically deplete the earth of valuable minerals, and this doesn't. This is completely renewable. And the second one is getting drinking water from contaminated water, which, you know, obviously is critical these days. And so the way it works is shown here. This is a naphion tube. And remember, in naphion tubes, you have an exclusion zone here, and all of the solutes, the junk, the bacteria, we could say microspheres, they're all pushed to the center. See, so the input flow can have lots of junk in it, but once it goes through the tube, the junk is confined to the center. So we built a collector, we call it a differential extractor. All it is two concentric tubes. So the one in the middle collects the concentrated stuff, the stuff you don't want, and the one at the edge collects basically it's easy water, which is essentially devoid of microspheres. We've actually, in a practical situation, we've gotten as much as a 200-to-1 separation between the two. So theoretically, it works very nicely, and we're trying to build up using this principle. The most exciting part is that we have some evidence, we're not sure, that salt can be separated from the water. So if you can imagine this inflow is ocean water, if it works as we think it might, we're still not sure, the salt should get separated to the center and get extracted in the same way as the microspheres get extracted. And this works, there's no physical filter in this. You don't have a filter that sits here that you have to change. And no energy. This works on the energy of the sun, which does the separation. So, and the places where water is needed the most are places where there's lots of sun and heat. So, conclusion is that, going back to what I presented, is that I think that we learned that there are three phases of water: ice, liquid, and vapor. But we have evidence for a fourth phase of water. And as I said, this is not a new idea. It's actually a very old idea that there's a fourth phase. And we think the structure of this fourth phase is very close to ice. And so if we, it turns out, we have experiments that demonstrate, if you want to freeze the water, you don't go directly from water to ice. You actually go from water to EZ and then to ice, you see. And it kind of makes sense because the structures are similar. And if you melt the ice, you don't go from ice to water, you go from ice to EZ to water. And you know, from the previous presentation about what happens in giving messages to water, I think the EZ is the one that is most receptive to information, as I tried to demonstrate. So it's no surprise that if the information comes into the EZ and the EZ forms ice, that the ice will have the information. So it's probably, we think, the EZ phase that is absorbing the information that goes into to create the different ice structures. So the implications, what I've shown you, the main and central one, I guess it's the take-home message, is that this water is absorbing energy from the environment all the time, and it has implications for biology, for example, for flow of blood, maybe for flow of lymph, which is not understood, maybe for flow of water up trees, which is also not understood. It has implications for chemistry because all of the things that I showed you today are not in the chemistry books, and if they're true, then a lot of things will change in the chemistry book. It has implications for weather because, you know, if you listen to the weather forecast, they'll tell you about the temperature and the pressure, and you've never, I believe, heard a weather forecaster say anything about the charge. The clouds are full of charge, and the atmosphere is full of charge, and I think it's going to turn out that charge is the most fundamental variable in determining the weather. And my new book that I'm working on has a lot of this information in it. And for health, well, I mentioned to you, our cells are filled with EZ water. If we don't have enough of it, we're dehydrated. The cells can't work when they're dehydrated because the proteins need to be surrounded by EZ water, and they can't do their folding if they don't have their natural environment. So we need to restore this water in any way that's possible. And out of this paradigm come a half dozen different easy ways, if you pardon the expression, easy, to build this kind of water in your cells, and should be good for your health. In terms of food, if you want to preserve the food, either by freezing or dehydration, you need to know something about what happens during freezing and what happens during dehydration. Practical uses for filtration, for maybe desalination, we hope, and for getting electricity out of water. So the next to the final slide is, I'm actually still within my time, our new Institute for Venture Science. And this is an organization that has nothing specifically to do with water, but it has to do with trying to fund promising ideas that challenge conventional thinking. We think this is critically important, and we just launched the Institute very recently. We're now inviting pre-proposals, 2-page proposals for some idea that you think will change the world, scientific idea that you can test. And anybody who knows some perhaps well-to-do people who want to do something meaningful for society, I think that science is going to be important in helping to prevent the imminent world meltdown that many of us are sensing. And the final slide, of course, is the book, and the book contains what I presented today, plus a whole lot more, because there's a whole lot more that it needs to be understood about water. So I hope you at least maybe take a look at it. The Amazon reviews have been very, very kind, and this was a labor of love that involved my son, the artist, and trying to present a message in clear language that's accessible to not just to scientists, but to everyone. I'll stop there. Thank you. Okay, thank you. Thank you. Okay.